Welcome back once again to another video. Today we're going to find the last three digits of, oh my god, what am I seeing here? 2023 to the power of 2024 to the power of 2025. Oh my god, this is indeed insane. I mean, this looks very weird. This is very crazy. How are we going to come up with the solution to this problem? Imagine raising just 2 to the power of 5. This will give us 32, right? You raise 2 to the power of, let's say, you're raising to the power of 9. This will give us 512. And you are asked to find the last three digits, which we have already here as 512. Imagine this number here. This number is extremely large. I mean, no computer on earth, I don't have idea, but I can talk the one I know. I can say the one I know. I don't think there's any computer that will give you the whole digits of this. Is that possible? I'm very sure Wolfram Alpha can give you the very last few digits. I trust Wolfram Alpha, right? Okay, I think at the end of this video, I will show you guys what Wolfram Alpha also got and if my solution is also right and corresponds with that of the Wolfram Alpha. But question here is this possible? Is this possible? Because this number is extremely large, right? This is going close to infinity. Is that going to close to infinity? Or let me mind my words. Okay, so what are we going to do and how are we going to approach this problem? So just stay tuned and watch this video from the very beginning to the very end, right? Because here we'll be making use of the Euler tangent function, or we call it the Euler-Phi function, right? So now we need to interpret this as follow and using the modular arithmetic. So this is same as 2023 raised to the power of 2024 raised to the power of 2025, then mod 1000. You know why I use 1000? Because the last three digits are asked, right? Assuming the question were what is the last digit of this number here, then we're going to make our mod a modulo 10, right? Or if it is the last two digits, so that would be 100. But in this case, we are asked for the last three digits, which we're going to make the modulo 1000. Okay, so let's see how we're going to approach this problem. Now let us recall the Euler-Phi, the Euler's tangent function, right? Okay, so the first thing we need to observe here is, for example, we have something like a raised to the power of the Euler-Phi of n is congruent to 1 modulo n. Here a and n are co-prime, right? They are co-prime positive integers whose GCD, that is the greatest common divisor of a and n, is equal to 1. You get the idea? Okay, now using this idea, now look at this base right over here. Then look at this 1000 right over here. You will find out that they are positive integers. In fact, they are co-prime, right? That is the GCD of 2023 and 1000 is equal to 1. You get the idea? Okay. So now, what next are we going to do? So we're going to find the Euler-Phi of 1000. Okay, so first of all, let us take note of some of the properties of this Euler-Phi function. So when we have the Euler-Phi of n and this evaluates to n minus 1, so this tells us that n is prime, right? So n must be prime for this to hold. So here we have the Euler-Phi of, let's say we have a to the power of b. So this will be equal to a to the power of b minus a to the power of b minus 1. So here, given that A is prime, you get the idea. So now we're going to evaluate the Euler fee of 1000. Oh, there is another property that I missed right over here, right? So that is that the Euler fee of a product A times B is same as the Euler fee of A multiplied by the Euler fee of B. So I missed this, or I forgot this anyways. So now this is equal to the Euler fee of 125 times 8 is same as 5 cubed multiplied by 2 cubed. Then using this one here, using this first, so this will be equal to the Euler fee of 5 cubed. You can see that the base is prime multiplied by the Euler fee of 2 cubed. Then we can use this one here. This will be 5 cubed minus 5 to the power of 3 minus 1, which is 2. Then multiply by 2 cubed minus 2 to the power of 3 minus 1, which is 2. Evaluate this. This is 400. Okay. So now we have to write that as 2023 to the power of 2024 to the power of 2025 modulo 1000 is congruent to 2023 raised to 2024 raised to 2025. So this power now will be evaluated in modulo 400, and do not forget that everything is in modulo 1000, right? Now let us concentrate more on this power. So we need to find 2024 raised to the power of 2025 modulo 400, which is same as finding the remainder when 2024 raised to the power of 2025 is divided by 400, right? Okay, so here now we have a problem, and what is that problem? Remember what we have there is 2024 to the power of 2025 mod 400. The problem we have here is that the GCD of 2024 and 400 is not equal to 1. So what are we going to do? So what we're going to do here is to split 400 as the product, as a product, I mean. And what is the product we're going to use? So we're going to use 16 times 25. 16 times 25. So what are we going to do now? So we're going to denote, let's call this one T of A is equal to, we need to evaluate 2024 to the power of 2025 modulo 16. And let's call T of B is equal to 2024 raised to the power of 2025 modulo 25, right? So for this part here, it should be congruent to 0. So which means 2024 to the power of 2025 divided by 16, the remainder is 0. But the $1 million question is, Shidex, how did you know about this? You know why? 16, we can still split that 16 as 2 times 8. Now, take a look. This base here has a remainder 0 when divided by 2. It also has a remainder 0 when divided by 8. So the smallest is 0. You can see. But this one here, we are lucky. You know why we're lucky? The GCD of 2024 and 2025 is equal to 1. Are we not lucky? We are lucky, right? Okay. So what are we going to do now? Then we're going to evaluate 2025 in modulo the Euler tangent function for 25. So first of all, the Euler tangent function for 25 is equal to the Euler tangent function for 5 squared, right? Which is equal to 5 squared minus 5 to the power of 2 minus 1, which is this. So this will give us 20. Hope you're enjoying the video. Something really new. If it is new, please comment. Like if you're seeing this for the first time and you enjoyed this video, please kindly comment. Please, you can like, give this video a thumbs up, you can comment, you can share with your friends, you can subscribe, right? If you really enjoyed the video, you can also send me a super thanks. God bless you, right? Okay, so now what is next? So here we have that T of B is equal to 2024 raised to 2025 in modulo 25, that this will be congruous to 2024 raised to, so 2025 now is a modulo 20, right? Then do not forget that everything here is a modulo 25. So for this part here, it is clear enough that that is congruous to 5 modulo 20, right? So that is the remainder when this is divided by 20 is 5. Is that 5? Is that 5? Yes. Okay. Okay, so now we have the power there as 5, so we say T of B is equal to 2024 raised to 5, then modulo 25. And this one here is congruous, is easy enough for us to write it as 24, then modulo 25. So you can check it out, right? Okay, so now we have the following. We get that T of A is equal to 0 modulo 16. We get T of B is equal to 24 modulo 25. So you know our next step now. Our next step is to find that smallest value for x, which has a remainder 0 when divided by 16 and a remainder of 24 when divided by 25. So with this now we're going to set the following systems of congruences, right? So we're going to say that x is equal to 0 modulo 16, or x is equal to 24 modulo 25. So now we have two systems of equation, right? And we're going to solve for x, the smallest x. We can actually find all values of x by generalizing, right? So but here we're going to find the smallest x. So now we're going to make use of the Chinese remainder theorem. So we call it the Chinese remainder theorem. Are you hearing that for the first time? So you see why mathematics is very, very interesting, and this gives me peace of mind. So that's why I love doing it, and by the way, I want to be a mathematician. Okay, so how exactly are we going to solve this? So now let me use the idea from Euclid, right? So now, see what we're going to do. We're going to make a substitution. So we're going to call x general solution. This will be 16 times a variable y plus 0. So there will always be a remainder 0, right? So remember we're adding 0, so this is just 16y. So we're going to plug in this equation. Let's call this equation 3 into equation 2 for x. The right answer will become 16y is, let's say, congruous, right, to 24 modulo 25. Okay. So now we know that 16y is also congruous. So adding the modulo here, 24 plus 25 plus, as you're adding, if you add 24 plus 25, you get 49. You add 49 plus 25, whatever you get, add 25, whatever you get, keep adding 25 till you get a multiple of 16. You get the idea? So now if you add that properly, you get a multiple of 16, which is 224, then modulo 25. So that is how it is done. So divide both sides by 16. You find out that y is congruous to what? 224 divided by 16 will give us 14 modulo 25. So put it in the general solution form for y. So get y will be equal to, so that will be 25 times k. Let us introduce another variable k, then plus 14, so there will be a remainder 14. So that's what you're seeing in there. Then let us recall back that x is equal to 16y. We should make the substitution for y. We get 25k plus 14. Opening the brackets, we get x is equal to the general solution. Isn't that cool? 16 times 25k, that will give us what? That will actually give us 224, right? Oh, sorry, I mean 400. Sorry for that. So 400k plus 16 times 14